Welcome back, everybody. We are now studying Newton's third law. Newton's third law says that for every action on one object, there is an equal and opposite reaction from that second object back onto the first. So we're going to see some very easy examples that I think you've got no problem with, and then we're going to look at something that's very, very simple but confuses a lot of people. So I want you to pay attention, especially to the second page. So let's do some easy ones. In the example below, the action-reaction pair is shown by arrow vectors and the action-reaction described in words. In A through G, draw the other arrow vector and state the reaction to the given action. Then make up your own example in H. All right, so let's see what we got. It says that the fist hits the wall. Now they did this one for you. And that the wall hits the fist. So let's go through the law that you've memorized and see if you actually are applying it correctly. For every action, an action is one object putting a force on another object. So for this action of a fist striking the wall, there's a force put by the fist on the wall. There is an equal and opposite reaction of the wall to the fist. So when you say action-reaction, there's always two objects involved. If there's ever a force on one object, two forces on one object, they're not action-reaction. Okay, it's not, because you actually have to have two objects involved in order to have an action-reaction pair. So a lot of these are very simple. So if your head bumps the ball, then you're going to have a equal and opposite force put from the ball on the head. So put that, ball bumps head. Okay, windshield hits bug. That means that whatever this vector is, that's what this vector is going to be the same. Bug hits windshield. Okay. Bat hits ball. Okay, so it's hitting the ball this way, so the ball is hitting the back that way. Okay. Ball hits bat. Hand touches nose. So nose, let's go an E. Touches hand. Hand pulls flower this way, so there's an opposing force this way. Flower pulls hand. Athlete pushes bar upward. I like that athlete part. Athlete pushes bar upward, so the bar is pushing the athlete's hand downward. So the bar pushes athlete downward, I guess. Compressed air presses balloon surface outward, so the balloon is pushing the air inward. So the balloon surface pushes compressed air inward. Okay, I'll let you do your own for H. Draw arrows to show a chain of at least 6 action-reaction pairs. Well, I've got a strong guy, and he is pulling on the string. The string is pulling on him. You can say that. Now, the monkey is pulling the string, and the string is pulling on him. Part of the string is actually being pulled by this guy, you can see. Likewise, okay, this is the string is pulling on him. He's pulling on the string. The string is pulling on the scale. The scale is pulling on the string. The string is pulling on the scale. The scale is pulling on the string. The string is pulling on the tree. The tree is pulling on the scale. Okay, you can't touch without being touched. Newton's third law, pretty cool. Okay, so please pay attention here because I think if you're not careful, you're going to get confused. Nellie Newton, here's Nellie, holds an apple weighing 1 Newton at rest on the palm of her hand. The force vectors are shown, the forces that act on the apple. All right, now notice that this is weight. What causes your weight? If you remember weight is W equals mg. Weight is gravity's pull on a mass. Okay, so what causes gravity? What's actually pulling on that apple? The earth. Okay, so what I don't want you to think is that this apple is pushing on her hand and the hand is pushing on the apple. That's absolutely true, but in this right here, as I'm asking you to think, the hand is putting a force on the apple. That's called a normal force. That's awesome. So that's on the apple. And it is true that the apple is putting a force on her hand, but that's not what I'm asking you to look at right this second. What's causing the apple to put a force on someone's hand? The fact that it has weight. So the weight is actually a force on the apple also. Now if I'm looking at her hand and it's touching her hand, I could have drawn it go to her hand and the hand push back up, and that would be an action-reaction pair. But if I'm only looking at the forces that act on the apple, if I have two forces acting on the same object, they cancel out each other and there is no action-reaction pair. Okay, so at this moment, I'm not looking at the weight pushing on the hand and the hand pushing on the apple, because that would be action-reaction. I'm talking about that the earth is pulling on the apple and causing weight, and that her hand is pushing on the apple and causing a normal force. All right, so if you can clarify that, I think you won't make some mistakes in a second. All right, so some questions. Like we said, she's holding an apple weighing 1 Newton. So 1 Newton would be a kilogram times gravity. Okay, 1 kilogram times 1 meter per second squared. So that would be about a small apple would be about 1 Newton. At rest in the palm of her hand, the forces, the vectors, are shown are the forces that act on the apple. So I've got two forces on one object, so they cancel out. To say that the weight of the apple is 1 Newton is to say that the downward gravitational force of 1 Newton is exerted on the apple by what? What's causing the weight? The earth. The earth is pulling on that apple, and that's what's causing it. Nellie's hand supports the apple with a normal force N, which acts in direction opposite to W. We can say that N, what? Equals W or has the same magnitude as W. Okay, so whatever weight is, that same magnitude, opposite to it is this. So it's the same magnitude. It doesn't equal W. It's the same as W, but it's opposite of W. The normal force, when we measured weight in order to find the normal force, we measured weight, found out whatever the magnitude of that weight was, and then the normal force is equal to that magnitude in the other direction. C, since the apple is at rest, the net force on the apple is, okay, it's not moving, so if it's at rest, the net force has to be 0. So far, so good? All right. D, since N is equal and opposite to W, we can say or we cannot say that N and W comprise an action-reaction pair. So here's where I want you to be careful. If W is being pulled by the earth and N by the hand, then I've got two forces acting on that apple. If these are the two forces we're considering, is that a action-reaction pair? No, an action-reaction pair, for every action that A puts on B, there's an opposite reaction that B puts on A. Okay, so that's really Newton's third law. The easy poem is for every action there's an equal and opposite reaction. But really what you have to think of, or you're going to get it wrong, is that for every action A puts on B, there's an equal and opposite reaction that B puts on A. All right, so both of these are on the apple, so that we cannot say that they comprise an action-reaction pair. The reason is because the action-reaction always does what? Do they act on the same object, action reaction, or on different objects? Always different objects. Here we see that N and W are both acting on the apple. For that reason, they're not action reaction. So in accord with the rule, if action A acting on B, then reaction is B acting on A. If we say the action of the earth pulling down on the Newton, or on the apple, reaction is the apple is pulling up on the earth. That is amazing. The fact that I'm pushing down on the earth with my weight and the earth is pushing up with my weight, somehow that's easy. That feels fine because I'm touching the ground and the ground's touching me. But if the earth is pulling on the apple with gravity, what you have to kind of leap, the next logical thing is that the apple is exerting gravity on the earth. Exactly the same. The same pull that the earth has on the apple is exactly the same pull that the apple has on the earth. Problem is the earth is so big that that force doesn't really do a lot of acceleration. That apple doesn't have enough tug on the earth to change the position of the earth. But the earth has that same tug on the apple, and because the apple is so small, it falls. This was the first line of thinking of Isaac Newton when he came up with the law of gravity, as he saw the apple fall from the apple tree. To repeat for emphasis, we see that N and W are equal and opposite to each other, and do what? Do they comprise or do not comprise an action-reaction pair? Back here, N and W. They do not comprise an action-reaction pair. Okay, so I'll let you read these. The cartoons are cool. So another pair of forces is N, okay, which is pushing up from the hand to the apple, and the downward force of the apple against the hand. All right, so this is a lot of people what you would imagine. That's an action-reaction hand. The hand is pushing on the apple is pushing on the hand. In this case, is it an action-reaction pair? Yes. If you're considering the weight of the apple shoving on the hand, a force on the hand, then suddenly it is an action-reaction pair. Suppose Nellie now pushes the apple up with a force of 2 newtons. So she's raising the apple. Okay. What happens if you put a net force on an object? Because you have the weight, essentially one weight acting down and 2 weights acting up, if you want to think of it as a magnitude. I have a net force of one weight, if you want, acting up. So it's one negative g, I guess. So is it still in equilibrium, or is it accelerating? If you have a net force on an object, it accelerates. And since you're putting that force upward, it'll accelerate upward. And compared to W, the magnitude of N, if it's 2N, has to be twice. Duh, that's obvious. Last one. Once the apple leaves Nellie's hand, so I guess she's tossing it up, do you see there is no more normal force? Because the normal force is caused by the interaction of her hand to the apple. So if there's no normal force, okay, the normal force is what's going up, it's weighting up, or it's the force going up, then what is the force going down? First of all, once it leaves its hand, there is no N, so that would be 0, and there is only W, only its weight is pulling down. Okay, so I hope that helps.